The U.S. Department of Energy's Spallation Neutron Source, or SNS, is located at Oak Ridge National Laboratory in Tennessee. SNS produces the most intense or brightest pulse neutron beams in the world. These pulses of neutrons are used in scientific research that affect our everyday lives, such as medicine, food, electronics, cars, and even airplanes. Neutron sources are used to understand and engineer materials at the atomic level. The SNS at Oak Ridge National Laboratory is a world-class facility for materials research based on neutron scattering. It consists of a negative hydrogen ion source, linear accelerator or LINAC, proton accumulator ring, liquid mercury target, and neutron detector instruments. In essence, the SNS is like a flashing strobe light, providing high-speed illumination of an object, giving scientists a view of each material's properties from the atomic perspective without damaging the materials. The nucleus, or center, of an atom is made up of protons and neutrons, with electrons rotating around the nucleus. In the universe, neutrons are abundant, but for research on physical and biological materials, neutrons of the right brightness are in short supply. Using the intense neutron beams of SNS, scientists can see the dynamics inside the atom and those of atoms joined together in materials. To produce intense or bright neutron beams, several stages are required. Amazingly, the entire neutron generating process for one burst of neutrons takes only 1/1000th of a second. To understand how this is possible, we'll start with stage 1, producing negative hydrogen ions. The ion source produces negatively charged hydrogen ions, meaning each atom has 2 electrons instead of 1 and 1 proton. The negative hydrogen ions are cut into mini pulses of 645 nanoseconds duration. SNS uses negative hydrogen ions because they accelerate well at stage 2 and can be efficiently injected into the accumulator ring at stage 3. Stage 2, the ions are injected into a linear accelerator, which focuses them into a beam and accelerates them to very high energies. Continued acceleration, up to 90% of the speed of light, is accomplished by superconducting cavities of niobium, a rare metal. These cavities are cooled with liquid helium to an operating temperature of 2 degrees Kelvin. A magnetic lattice, or giant magnets, focuses and steers the beam through the cavities. The energetic beam from the linear accelerator enters an accumulator ring at stage 3. The ions are passed through a carbon foil which strips off each ion's 2 electrons, converting it to a proton. The protons continue in the accumulator ring where they accumulate in bunches. The protons are accumulated for 1046 turns through the ring, with more protons from the linear accelerator joining each turn. Protons are painted or spread out as they accumulate to allow them to hit a larger area of the target. Following accumulation is stage 4. Where each bunch of protons is suddenly kicked out of the ring, producing a pulse directed at the target. Each pulse is less than 1/1,000,000th of a second. That means a new pulse will hit the target 60 times a second. The high-energy proton pulses strike the heavy metal target, a container of liquid mercury. When the protons hit the target, the mercury's nuclei are excited, releasing millions of neutrons. This reaction process is called spallation, hence the name Spallation Neutron Source. Stage 5. The millions of neutrons are formed into high-intensity or very bright beams. However, for research purposes, the beams have to be cooled. For some experiments, beams are passed through cells filled with water, slowing down the beam and cooling it to room temperature. For other experiments, the beam is passed through containers of liquid hydrogen at 20 degrees Kelvin, needed to produce cold neutrons. Now, we are ready for materials research. These room temperature and cold neutrons are guided to the neutron detector instruments for scattering experiments on a multitude of materials. The SNS instrument hall will eventually contain 24 instruments on 18 beam lines. The whole process of acceleration, accumulation, extraction, and delivery to the target is repeated at a rate of 60 times a second. The SNS will produce pulses of neutrons every 17 milliseconds, producing 10 times more neutrons than are produced at any other pulse neutron source in the world. Research at the SNS is also playing a key role in developing solutions for energy needs, environmental protection, and the problems of global warming. For more information on SNS and neutron sciences, visit www.ornl.gov. For more information on how the Spallation Neutron Source can bring tomorrow's science into today's classrooms, contact Marie Westphal at ORAU's Center for Science Education.